And currently we're involved in a research project to evaluate the flashing yellow arrow signal display installed at for the left turn interval in the Peoria area, and that project is funded by IDOT and the ICT. So as a part of that, we presented our preliminary results at the TRB because the study is still ongoing. I'd also like to acknowledge my co-authors on the paper who were involved in the project, Jessica Lund, William Lorton, and Bo Burdett. Ultimately, where we began with this project is a concern for left turn crashes and the left turn movement at signalized intersections. This isn't an area-wide situation. It's a phenomenon that occurs throughout the U.S. Essentially, if we take a look at our crash statistics, 27% of our intersection crashes involved left turners, and 2/3 of all of those occur at signalized intersections. Often during the permissive left turn phase where drivers are to negotiate a gap in traffic, and if that gap exists, then they could complete their movement. That's in contrast to what we call a protected phase, where in that case a left turn driver would be given exclusive right-of-way, typically by a solid green arrow indicating that that driver could complete his or her turn. Really, throughout the U.S., there are many different states that follow many different practices and utilize a variety of signal displays for the permissive left turn indication. Predominantly now throughout the state of Illinois, the circular green with supplemental sign is used. However, other areas would use a flashing circular yellow. A lot of states now have been investigating the flashing yellow arrow. However, traditionally, some other states like Michigan used a flashing circular red, and others used a flashing red arrow, all to indicate the same message for the permissive left turn. In that case, there was a lot of concern for this non-uniformity, and the National Committee on Uniform Traffic Control Devices commissioned a study through the NCHRP, which was documented in Report 493. This report took place, or actually was published in 2003, and as a part of that, the researchers there were investigating what is the best message, what is the best mounting display. They looked at a variety, an exhaustive set of criteria and conditions, really just to evaluate protected permissive left turn control at signalized intersections. Their results in 2003 found that the flashing yellow arrow is well understood by drivers, and they recommended its application further. As a result, then now forwarding to 2009, the MUTCD adopted the flashing yellow arrow as a permissible option. Then, in 2010, IDOT, and specifically this is mostly in District 4, decided to install over 100 flashing yellow arrows in the Peoria, Illinois area. And really what they did also is to change the signal itself, so it went from a 5-section signal head with circular green to 4-section signal head with flashing yellow arrow. As a part of that change, the operation, no changes were made to the operation. So if they were protected permissive in the before condition or when the circular green was in operation, they were also protected permissive with the flashing yellow arrow. Our research goals then, after the project and after the flashing yellow arrows and signals were installed, we were retained through the ICT, working with IDOT, to evaluate the effectiveness of the flashing yellow arrow specifically for permissive protected left turn control. We went with a 3-tiered approach. First, since it is a new indication and a new message, we did a driver understanding survey to see how they felt or how they understood in a static environment the message of the flashing yellow arrow compared with other messages that they may see out on the road. we also went out and performed some field studies at the test locations, those where flashing yellow arrow was implemented. However, we utilized a before and after evaluation methodology. So we went out and collected video data on driver behavior before, when the circular green were in operation at a sample of sites, and then went out once the flashing yellow arrows were operational and collected the same data again on video, brought that back and evaluated it. The rationale for that, for the traffic operation, is that IDOT was interested in having some preliminary results and indication on how they were working, because really the ultimate goal would be to evaluate the impact of these flashing yellow arrows on safety or on traffic crashes, which is still ongoing, and that's what we're involved in for the next few years. But really the issue here is that it takes more time to accumulate crash data, and we wanted some preliminary results in advance. So this presentation will focus on, and the paper that was published in the annual meeting of the TRB is going to focus on the driver comprehension survey and the results of the field operation and traffic conflict study. Our crash-based analysis is ongoing and was outside the focus of the paper. So the results of the driver understanding survey is what I'd like to share next. Ultimately, we wanted to have an indication of how drivers understood the flashing yellow arrow, and in this case, we came up with mostly it was a static survey. However, we did have some flashing modes being animated. We obtained not only demographic information about those responding to the survey, but also very specifically how they would respond to a variety of static left turn scenarios. Overall, we disseminated this survey in 2 different phases. The first phase was 5 months after the initial flashing yellow arrows began to be installed, and out of that phase we received 127 responses. And then we thought we'd like to, maybe after some time had passed, to allow drivers to get used to the flashing yellow arrow to see if there was any difference in their understanding of what the proper decision to make would be. Phase 2, then, we reposted the survey 16 months after the flashing yellow arrows, or 11 months after the phase 1, and out of that we received 236 responses. And here in Table 1, what you can ultimately see is just the demographic information of the participants from the survey. These are examples of the screen that the participants would also see. Mainly, we were asking them, when presented with a variety of scenarios, if they wanted to turn left and saw the traffic signals shown in the photographs, what would they do? And the choices were to go because they had right-of-way, to yield and wait for a gap, or to stop and just wait for a signal. Overall, we utilized 7 different left turn scenarios. The previous slide just showed 2 sample ones. We included some that involved the green arrow, which is exclusive right-of-way, meaning that the drivers could go. We see that option in Scenario 1 and Scenario 5. Then, because of the operation that we have here in town, there would be some instances where drivers would see the flashing yellow arrow, meaning they could go if they found a gap. However, their through counterparts, the vehicles just sitting next to them in the adjacent traffic lanes, received a red signal indication. That scenario specifically is Scenario 4. So what you'll see in all the scenarios, really what we're trying to do is vary the message, at least for the permissive indications among circular green, flashing yellow arrow. Also vary the through signal indication, being either red or green. And then also here, the installation of the flashing yellow arrow at about half of the intersections, they received a supplemental sign that would instruct the driver what to do. And you can see those in scenarios 6 and 7, where the sign reads left turn yield on flashing yellow arrow. Some of them had the symbol, some of them just had text. At other locations, there was no supplemental sign at all. It was just the flashing yellow arrow. So we wanted to take the participating drivers through all of the scenarios to have an understanding of their comprehension. Overall, we took a look at the results of phase 1 to phase 2 to see if there were any differences at all. We used a statistical test, and specifically the chi-square test, to see if there were differences in the correct responses among the scenarios just between phase 1 and phase 2. Ultimately, there was really not more than a 3% difference, and statistically, the results proved that there was no difference really in the respondents between phase 1 and phase 2. So we were able to combine the results and continue into further analysis from there. All right, so now what you're seeing is both phase 1 and phase 2 combined, the total percentages of the 363 drivers that responded in both phases for all of the 7 left turn scenarios. The correct answer for scenario 1 and 5, I'll just jump back, would be to go, because in 1 and 5 they have an exclusive green arrow, or that would be during the protected phase. For the remaining, those are all permissive phasing. So for the remaining scenarios, 2, 3, 4, 6, and 7, the correct answer should be yield. All right. And in that case, we can see some of the varying responses. Overall, the vast majority of drivers understand what the correct message is. We do see some lower correct response rates of yield at scenario 4 and scenario 7. So if we go back, scenario 4, there's no supplemental sign provided and the adjacent through is red. Scenario 7, the adjacent signal is red and there is a sign. So that would tell us that drivers may experience some confusion when the adjacent through traffic displays a red signal, because they have never experienced that here in town. It's just a new method of phasing that we're able to do because of the flashing yellow arrow. We then subjected all of these scenarios to statistical testing, and in this case you can see all of the different scenarios that we went through and the focus of those. So we wanted to ultimately determine the effect of the flashing yellow arrow with and without the sign, as well as the effect of the flashing yellow arrow when the adjacent through signal received a green versus the through receiving a red signal. And we compared those with also we compared them with the circular green message, and at the bottom we did a variety, just kind of a cross-check of scenarios combined to illustrate a point. We not only looked at the percent of correct responses, we also looked at not necessarily just the wrong response, but a wrong response that was a go when the answer should have been yield. So we, and others have coined that term, fail critical response. In contrast, the other wrong answer could be considered a fail-safe response, meaning they could have yielded, but they chose to stop. But there would be no safety implications there, just implications on efficiency, ultimately. In our analysis, we just looked at the percent correct response in those comparisons, as well as the percent fail-critical responses. In all of those, we used the Z-test for proportions at 95% level of confidence. And we got a variety of different findings. We did find a lot of significant differences, though, in driver responses to the survey. And although the specific data is contained here, we're able to just summarize our findings in the next few slides. So based on the fail-critical responses, there were significantly higher incorrect go answers for the circular green compared to the flashing yellow arrow when the flashing yellow arrow also had the supplemental sign. So that indicates to us that under some situations, driver may be confused about the message of the permissive left being green, thinking that they could go. However, according to the correct responses, we saw that, well, drivers had significantly higher comprehension of the flashing yellow arrow when the adjacent through traffic received a green signal compared to a red signal, regardless of the supplemental sign. But we couldn't confirm that in terms of any negative responses or incorrect responses that were received from those questions. We also found that the supplemental signs were beneficial in the driver understanding survey. When the supplemental signs were presented, in addition to the flashing yellow arrow, there were significantly higher number of correct messages, regardless of the color of the adjacent through signal. It was also found that there were less incorrect responses or those fatal incorrect responses, meaning that they would go when the sign was present. So we do see some benefits, at least from the driver understanding survey, of providing the supplemental sign along with the new message. We feel at this time we're not ready to make firm recommendations on the sign until we see the results of the crash-based analysis, because in a closed, static environment, just because drivers say they would respond one way, doesn't necessarily that would mean how they would respond in a real driving experience, and also we don't know what the impact would be on crashes. So moving on to the traffic operation analysis, we studied a variety of different variables in this case. The variables that we focused on were critical gap for the left-turning vehicles, meaning the size of the gap that a driver turning left accepted to complete the turning movement, but that gap existed in the opposing through traffic stream. Okay, and we looked at the median or 50th percentile of the data to assess the critical gap per classic definition. We also looked at yellow light runners and red light runners. Here we wanted to really use the operational data as a surrogate to crashes or as preliminary results while we're waiting for the crash data to accumulate. So in that case, red light runners ultimately do not have high frequency overall. So we decided to tack on those that are completing the turn in the last half of the last 2 seconds, say, of the length of the yellow, just as another indicator of understanding and behavior and potential safety implications. So we did red light runners following the permissive left turn phase. We did red light runners following again the permissive phase, and then for those experiences following the protected phase, we combined the yellow light runners and the red light runners together because when we had the circular green operation, there was a pseudo all red interval in place, but it wasn't apparent to the left turning drivers themselves. So we did not actually see when the circular green or in the before condition, we didn't see a red, although there was what we call a pseudo all red in operation from a safety standpoint. So that's why we had to lump the yellow light running and the red light running following the protective left turn phase. We also looked at traffic conflicts. What we did, we selected 16 sites and collected a total of 128 hours before and after the flashing yellow arrow was installed. We had 64 hours of before data, so that's 4 hours at each of the 16 sites for both the before and the after period. Then for all of those variables, we used the t-test statistic at 90%, 95% level of confidence to come up with some conclusions on what is the operational and safety impacts of this change. For the critical gap, the data that we came up with, now this is aggregated for all sites and all data points, and in this case, we did not find any significant change in the size of gap that a driver accepted to complete the left turn, circular green versus flashing yellow arrow, or before and after. So we saw no impact for the variable of critical gap. Looking at the yellow light running and red light running following the permissive and then following the protected phase, here we really saw mixed results. And one other, we decided to come up with more than one variable to describe the phenomenon. So we considered, for example, yellow light running per hour, and in this case, the table shows the average occurrence per hour for both the before and the after period. Then we thought maybe it could be a function of the left turn volume itself. So another variable we had left yellow light running per 100 left turning vehicles. And then finally, we thought it could be a function also of the opposing through. You know, the behavior of a left turning vehicle could be influenced by the opposing through volume. So in that case, we're using per 1,000 opposing through vehicles. And the rates are all provided. In this case, for yellow light running, we didn't see any significant difference between the before and after periods. For red light running, following the permissive left turn phase, again, among the three variables, we only found one significant increase. So that would mean that the average red light running per hour following the permissive left turn phase increased with the flashing yellow arrow. For the other two variables, however, that consider exposure, there was no significant difference there. When we look into the red light running and yellow light running combined following the protective left turn phase, for all three variables, we didn't find any significant differences. So overall, we found out of all of that just one significant finding, but in our opinion, that may not be quite enough to really make any profound statements that, in terms of from a safety standpoint, it could just minimally impact driver behavior related to red light running. We then looked at traffic conflicts, and here specifically, the conflicts that we analyzed are listed with a few diagrams to show what we were looking at, and this again at the 16 sites from a before and after standpoint. We looked at the conflicts on a per hour basis, per 100 left turning vehicles and per 1,000 opposing through vehicle basis, and we didn't find any significant differences in the conflicts themselves. Although we do visually see some reductions in the numbers if we look before and after, however, we're not able to attribute that to anything related to the project. So overall, with this study, you know, we saw that drivers have a high comprehension and acceptance of the flashing yellow arrow message. We didn't see any negative impacts related to traffic operations. We did see some evidence that the supplemental sign could help drivers understand what the appropriate action is to take at the intersections, but ultimately we are awaiting our comprehensive crash-based analysis to make more substantive conclusions about their effectiveness. I'd also like to thank the ICT, our technical review panel, and specifically Mr. Randy Laniga, who is the chair, as well as the committee itself, you know, for all of their technical guidance and support throughout the project. And at this point, I can take any questions that you may have.
Okay, I just unmuted everybody, so if anybody has any questions, this is the time to ask.
Kerrie, this is Katie. I'll ask a question. It appears that the flashing yellow light means the same thing as what traditionally we've seen as a solid green light, and you want to make a left turn, that you need to watch and make sure that it's safe, and then you turn. So I'm assuming that the reason that you're investigating this is because research has shown that there is safety in having the flashing yellow light rather than just the green?
Well, you're correct. Yes, the message is the same for the flashing yellow arrow and the circular green. Really, back in 2003, the NCHRP 493 researchers felt that under the wrong context, when a driver approaches an intersection and sees the, the solid circular green with supplemental sign, our brain tells us green means go. So they started questioning the overall effectiveness of the circular green as the best message. So they're suggesting that the flashing yellow arrow is a better message. And we're evaluating it here in Peoria.
Okay.
Yeah. I know some drivers don't like any change though.
Right.
And I've heard many different comments of their opinion. But now a lot of our drivers are getting used to it, and actually the flashing yellow arrow is being installed in about 31 different states at varying levels across the U.S. Some states have over 600 signals with them operational, and I think ultimately at a national level what they really want to get to is uniformity. Not you have to understand a red flashing ball in Michigan, and in Maryland maybe you have to understand something else, that it'll take time and transition, but I believe, that was the purpose of the 2003 study, is to determine what is the best message, regardless that the circular green is probably the most predominant message being used, or at least at that date, at that time.
Interesting. Thanks.
Sure. Thank you.
Any other questions? Okay, looks like that's it for our questions. Thank you, Kerrie.
Okay, well, thank you.
We'll begin our second presentation now.
Okay, can you see my presentation all right? Annie, can you see it okay?
Yes, sorry, I muted myself.
Okay, thanks.
We can see it.
All right, great. I'm Katie Zimmerman, and I'm the president of Applied Pavement Technology, and today I'm going to be talking to you about a project that was sponsored by ICT, and it was involving the implementation of pavement management systems for local agencies. And we had a team of researchers, not only from Applied Pavement Technology, where Angie Walters was our lead, we also included Bradley University on our team. And Kerrie Schattler, the previous speaker, led the Bradley University efforts there. But we also had Ashley Reegraff, who was a graduate student who participated and helped tremendously with the project results. We also had a technical review panel, and you can see the members of the technical review panel shown on the right. Kevin Burke was the chair of our technical review panel. The objective of the project was to help establish some guidelines that local agencies could use for implementing pavement management systems. Within those guidelines, they wanted us to document the implementation process so a local agency would know what's involved in the implementation of pavement management. They also wanted us to provide details on the types of systems that are available and the amount of data that might be needed to support those systems. And also to talk a little bit about some of the implementation successes and challenge that agencies had run into. The project consisted of two different phases, I'd say. The first was a synthesis of the state-of-the-art and the state of the practice. And the second phase was actually the development of the guidelines based on what we had learned in this first phase. And I should mention that Bradley was largely responsible for conducting this state of the practice synthesis that was produced. We actually published a separate document that summarizes the results of the synthesis, and a copy of the report is shown on the right. The content of this report included a summary of some of the pavement condition survey methodologies that are being used, a summary of the pavement management software programs that agencies are using, and a broad summary of some of the national pavement management implementations that had been done across the U.S. We also did a much more detailed survey of local agencies within the U.S. so that we could get a feel of what's the state of the practice here in Illinois. And for some of the people that participated in that survey in Illinois, we developed a few case studies. As part of the synthesis of state practice, one of the topics that we looked at were the pavement condition survey methodologies that are being used. And we found that there are several different approaches that are being used for pavement management. First of all, in terms of way of collecting, we found that agencies were either doing manual or automated surveys. We also found that in terms of the types of distress information that was being collected, in some cases they're actually measuring the different distresses and using that information in determining the condition of a section. But other agencies were using an approach that's represented by the graphic on the right, where they might be estimating the amount of distress, or they might be using a rating like this, which is from the PACER rating manual, where they're given a particular rating, in this case it's a 5, and there's a description of what the distresses look like, what you would see in the field if you saw a pavement that was in a condition rating of 5. And the pictures help you visualize to see whether what you're seeing in the field matches up. Now, as you could imagine, this is going to be a faster, easier survey to do, but it's also going to be a little bit more subjective than a survey in which you actually measure the distress quantities. We found that there are a number of different pavement management software programs that are being used. There are both public and private software programs. Among the publicly developed or public domain software programs, there was one called MicroPaver that was developed by the Corps of Engineers. There's also other programs, RoadSoft GIS, which came from Michigan's Technology Transfer Center, StreetSaver, which was developed by the Metropolitan Transportation Commission in the San Francisco Bay Area, and then the Utah Technology Transfer Center had a program called TAMS. We also saw that there were a number of private or proprietary systems that were included, and in particular we looked at those that are named Pavement View, PavePro, PubWorks, and RoadCare. The survey of practice found documentation for 24 different city and county pavement management programs across the U.S. Now, we recognize that there are actually a lot more pavement management systems implemented in the U.S., but one of the challenges that we faced was that not all of them document their process or have that type of information available in the literature. So this is a representation of what we found that was actually documented. And you'll see that it represents a range of different sized agencies. These agencies took a number of different approaches to the implementation. Some did the implementation themselves. Others hired consultants to help them. We had a range of different pavement condition survey procedures that were being used and a range of different software programs. Now, we also took a look at what's going on in Illinois in the local agencies across the state. And we sent a survey to 347 different municipal and county engineers in the state of Illinois. We received back 115 responses to the survey. And of that, 59% of the agencies that responded did have a pavement management system, and 41% of those did not have a pavement management system in place. We presented in the report a number of different summaries of the information that we obtained from the state survey. But a couple of things that we wanted to highlight are shown here. One is that on the left-hand side, you can see a summary of those agencies that had implemented a pavement management system. What was the size of that agency? And I think it's pretty obvious from this graphic that it wasn't just the large agencies that had implemented pavement management. There were also a number of smaller agencies that had been successfully implementing pavement management. On the right-hand side, you can see the size of the network. And so, again, you can see some support for smaller agencies having implemented pavement management. We looked at the length of time it took them to implement pavement management, and the responses show us that about 48% of the responding agencies indicated that it took them about 10 years to get fully implemented. So what that shows us is that if they're trying to do it themselves especially, it does take time for you to fully implement and take advantage of the capabilities. Some of the others that were able to do it more quickly either had resources that were focused on the implementation of pavement management, or they might have used a consultant to help them along with the implementation process. We also show here that a large number of the agencies were part of a metropolitan planning organization. As I mentioned, there were a number of different software programs that we found were being used here in the state of Illinois. And if you look at the first two columns here, you'll see that these are agencies that are using spreadsheets for their pavement management system. In one case, the spreadsheets were developed internally. That's the larger of the two bars. And the second one shows that that was something that was developed externally for the agency. In terms of the software programs that are not spreadsheets but are more pavement management systems, MicroPaver was the most commonly used software tool here in the state of Illinois. But there are others. The PavePro program was significant and mentioned by a number of agencies that it's being used. But the programs, the last four programs on the right-hand side are more the proprietary type systems. We also looked at the way that they're conducting their pavement condition surveys as part of their pavement management system, and we found that the majority of agencies are doing some type of windshield survey where they're driving over the pavements and making an assessment of the condition. There were a good number of people that were doing walking surveys where they are actually measuring the distress information, but there were also a significant number of agencies that are starting to use automated vans, which are configured with lasers and digital cameras that drive over the pavement and collect the information at near traffic speeds. In terms of what they do with the data that they collect, the most common approach is to convert that information into a pavement condition index, or a PCI, as shown on the right-hand side. Another large number of the agencies just use that distress information to rate whether the roads are in good, fair, or poor condition. And we did see a significant number of agencies using that PACER manual that I showed you earlier. So those seem to be the most common. And we did see that there were a couple of agencies that are using more than one data collection procedure as part of their process. From the participants that answered the survey, we did select a number of them and featured their stories as case studies in the report. From the municipalities, we featured Macomb, Naperville, and Villa Park. And in terms of the counties, we went to Champaign, Edgar County, McHenry, and Stark County. And we selected those because they represented a range of, very urban and very rural communities. We saw a number of different sizes of agencies, and we saw different approaches to how they were doing pavement management. So we were really trying to represent a broad cross-section of different types of approaches that could be followed. Now, we don't have time to discuss all of the case studies in detail, so what we included here were some of the key quotes from those agencies that we had talked to. And I think there's a couple of things that are important to call out here. The first one from the city of Naperville. They point out that the fact that the economy is in a certain situation where money is harder to come by. So because of that situation, the pavement management system has become even more important to them. We saw in Champaign County, they told us that they were now able to reduce political pressure, which is important to a lot of local communities. And in Edgar County, the comment that they made was it helps them do the right work at the right time for the right reasons. So again, focusing on the fact that they're looking more at the engineering side of what's needed for the roads, maybe rather than the political side. So that's a brief overview of the synthesis that was developed as part of the project. The second product was an implementation guide, and this guide was developed to provide help and guidance to local agencies who are hoping to implement pavement management or advance their implementation efforts. This is the content that was included in the implementation guide, and as you can see from this, at the beginning we were really trying to introduce local agencies to pavement management and the benefits and costs that are associated with pavement management. We wanted them to understand why it's worth the investment to put your money into pavement management and collect that information. I'd say the bulk of the report is focused on that Chapter 5, Designing a Pavement Management Process, and I'm going to talk about that part in a little bit more detail. First, though, I want to provide some of the highlights that were included in the guide as to why should you even invest in pavement management. And on the left-hand side, you can see we've included in the bullets a couple of the reasons that it's really important to use pavement management. It provides an agency with a way to rationally and objectively differentiate between the needs and decide what's the best way to invest your funds so that you get the optimal return on your investment. It helps you identify the best treatments for the conditions that are out there, and by doing that, it helps extend the life of the road so that you get better performance over a longer period of time. But one of the other reasons that some agencies found importance in investing in pavement management was it really helped their credibility and enabled them to be able to tell their story, communicate their needs to different stakeholders. And along the right-hand side, you can see some of the actual quotes that agencies came up with to support some of those points. The primary emphasis was on this pavement management process, and what we included in the guide is a 7-step process for pavement management implementation. And I'll go through each one of those steps pretty quickly. First of all, you've got to establish your inventory. So you have to define what the network is and collect certain information about the data. The minimum requirements is really that you know what the road is, where it's located, you have some idea of the dimensions, you know what type of road that is, and you need to have some idea of when it was last constructed. So that's really the minimum information that's going to be required. If you can provide other information about your network, that's going to be great, and it's going to enable you to make better and better decisions. But it's not absolutely required in order to get started. One of the things that we did in this guide was we tried to look at the implementation of pavement management from 2 different perspectives. One is an agency that might be a smaller agency or an agency that has limited resources. How could they get started in pavement management? And then secondly, we looked at some of the larger agencies, or an agency that wants to get started or an agency that wants to make their system a little bit more sophisticated. And so throughout the guide, we included 2 different approaches that an agency could take, one of them more on the simplistic side and one more on the sophisticated side. And so even a smaller agency that really didn't have a lot of resources to put towards pavement management could get started. So in the two different approaches for defining your network and collecting the data, if you really want to start from a basic perspective, you might just estimate some of the initial data because you don't have readily available information. And as you get to be familiar with the system or as you update your work over time, you can update that information and the assumptions that are being used. If you have more resources, you might actually go out and collect information about the assets that you have. This is going to be more time-consuming in the beginning, but it is going to give you more accurate information. And there were a couple of resources that are available to agencies that wanted to do this. For example, the Illinois Road Information System and the GIS files that are available at IDOT were one source of information to help agencies with this inventory activity. For collecting pavement condition information and conducting surveys, the two different approaches, one is where you're actually estimating distresses rather than actually measuring it. And there are two approaches that are available. IDOT's CRS manual is one approach for estimating distresses, but also the PACER guidelines that are available, I believe, from the University of Wisconsin is where you can get those. If you want to look at that, it's more geared towards local agencies. The second approach, if you have the resources, available to be able to measure the distresses, you might do something more like the Pavement Condition Index, which requires you to identify the type, severity, and amount of distress that's identified in the field, and use that to calculate an index on a scale of 0 to 100. So that would be a more resource-intensive approach to collecting data. And there's really a trade-off between collecting all the information that you might need to make good decisions and being able to collect that and maintain that information over time. So you really got to figure out what resources are available for this activity and how can I maintain it with time. The second aspect of collecting condition information is whether you're going to do the surveys manually or whether you're going to try to use automated equipment for that. And the guide includes some advantages and disadvantages to each approach. For example, the manual method is fairly simple and it doesn't require a lot of capital in order to be able to do that. However, the automated is going to be safer because you're not going to have your people out on the roads, but you might need a specialty firm or specialty equipment in order to be able to do it. Once you have the condition information, then you can predict conditions and forecast how the conditions are going to change with time. And performance models are really one of the fundamental aspects of a pavement management system. This is a key and what really sets it apart from a database. So performance models help you identify when is the right time to apply a treatment, or in the future, what kinds of treatments are going to be needed. Because you can predict future conditions, it allows you to do what we call what-if scenarios, where if I invest different amounts of money, I can see what my predicted conditions are going to be into the future. And that allows you to demonstrate some of the consequences of different investment strategies. So if somebody is wanting to cut your budget by 10%, you can show the long-term implications of that decision. There are two different approaches that you could use to develop these performance models. The simplest of the two approaches is just to use an average rate of deterioration for your roads. For example, you might say that your asphalt roads deteriorate 3 to 5 points per year, and you can then forecast how that's going to change over time. But you can also use historical condition information and develop very sophisticated statistically prediction models that will allow you to forecast those conditions. One of the other steps in the implementation of pavement management is to identify the treatments that are going to be considered, and you have to come up with some rules for when those treatments are going to be applied. Probably the simpler approach is to develop some treatment cycles. So, for example, you might say that you're going to do a chip seal every 7 years on your road. And so you can map that out as to when that treatment is going to next be needed and allocate funding for that. Some of the more sophisticated pavement management systems allow you to make treatment rules that define the condition at which different types of treatments are going to be applicable. And as you can see from this graphic, as a pavement ages and as the condition deteriorates, the types of treatments that are appropriate are going to get more substantial and more costly. You usually have more needs than you do dollars available, so you have to have a way of deciding which of the projects should you fund. So included in the treatment selection portion of the guide are two different choices for selecting projects. The simpler of the two is a ranking process. Many agencies rank based on the worst roads are going to get funding first, and that's actually a very costly way to manage your network. What's more cost-effective is to do something like the benefit-cost analysis that's shown here on the slide, where you can figure out and represent the additional life that a treatment is going to get you, and if you divide that additional life by the cost of the treatment, you get what's called a benefit-cost ratio that tells you, in essence, how much bang you're going to get for your buck. So if you can choose those projects that have the highest benefit-cost ratio, usually you're going to be making a better investment. Whichever approach is used, I think the key is really to move away from a worst-first approach, because that's a very expensive way of maintaining roads. You might think about it like if you bought a new car, and if you didn't do any maintenance on that car and you just waited for the engine to go. That's kind of a comparison to what it's like to not take care of our roads and just wait until they deteriorate. We also included in the guide some ideas about different types of reports, and depending on what it is you want to get out of the pavement management system, the approach that you're going to take might differ. In this case, on the left-hand side, we see a summary of the percent of the area in different condition categories. So that's a pretty basic report that can be generated. On the right-hand side, we see forecasted conditions under 3 different budget scenarios. So this kind of a forecast is going to require you to have performance models in place and treatment rules that will allow you to do this type of thing. So depending on what it is you want your pavement management system to do for you, it might influence the approach that you're going to use for the condition survey or the software. One of the common methods that we saw a number of agencies using for presenting their information is in GIS and using the mapping process to be able to display different types of information. The final step in this, or the second to last step in this, is to actually select a pavement management tool. And we included 3 different approaches. One, that's the spreadsheet or GIS. Secondly, public domain software. And finally, proprietary software. And we put that into a graphic that looks like this, where you can see in the center of the page are the 3 different types of software. They're represented by columns. So one is a spreadsheet column, one is a public domain column, and the other is a proprietary column. And what we were trying to show here is that as you are using more of the more basic or simplistic approaches for doing your network inventory or estimating the condition of your pavements, you're probably leaning towards more of the spreadsheet or maybe public domain software. However, if you want to have very sophisticated performance models, you want to use automated data collection and actually measure your distresses, you want to do a benefit cost analysis, now you're moving towards either the very sophisticated public domain software or some of the proprietary software. And so we tried to use this graphic as a way to represent which type of software might be best for each agency. It also shows on the right-hand side step 7, which is keeping the process current, so making sure that you're continually updating the inventory with new information. I think just in wrapping things up, what we hoped to show with the guide is that pavement management really makes sense and that every agency can get started. Whether you want to start very simply, whether you want to do something more sophisticated, there are different tools, different approaches that you can use and be successful. I did include the link for the reports that are available on the ICT website, and it is report R27-87 if you want to see which reports to order. So with that, I'll sign off, and if there are any questions that we have, I'd be happy to try to answer them.
Okay, I'm unmuting everyone now. Thank you for your presentation, Katie. If anybody has any questions, this is the time to ask.
Sorry, Katie, I don't have questions at this time either.
All right.
It's Kerrie.
Oh, Joe's typing something, I see.
Oh,
shoot. Joe.
Okay, so it looks like we have no questions. Thank you, everyone, for joining, and thank you for your presentations, Kerrie and Katie.
All right, thank you.
Thank you. Have a good day.
You too.
Bye-bye.